An ohm is a unit of electrical resistance. What you're measuring is resistance. I'm going to write that word here. You're measuring resistance in ohms. And what that funny looking space alien is doing there is that's the symbol for the unit of measurement. It's a Greek letter. It's the Greek capital omega, uppercase omega there. You can see that one says ora, meaning hour, or meaning time, and the English word hour is coming from it. There, Greek alphabet. Uppercase, they have a whole alphabet, uppercase and lowercase. You might see this lowercase for angular velocity, also omega. Alright, that's other physics. So, for example, you might say, to use it in a sentence, that the resistance of something is 5 ohms. You can write ohms that way. You say ohms, but you write the Greek letter omega, uppercase. So, ohm is a strange word. It's named after a 19th century scientist. I wrote his name up there. His name is Georg Shimon Ohm. Alright? That's the dude's name. And how this works is fairly straightforward. We're going to discuss conductors and insulators and resistance. In a conductor, such as a metal, the resistance is low. The material lets through electrons really easily. In an insulator, where the resistance is high, it takes a whole lot of effort to make the electrons move inside the material. I'm going to explain this one just a little better. There, here is periodic table of elements. All kinds of elements, solids, gases. Okay, yep. When elements solidify, they're gonna take up a crystal structure. You can see some of the crystal structures here in these pictures, where the atoms would be at the corners of a crystal. When the element solidifies, it just takes up that crystal structure, or that crystal structure, just like bam, the atoms know where to go on their own, and they just pick up that structure and they line up like so. For example, here is aluminum or aluminium, depending on where you're watching, and it's marked with that symbol, so that's gonna be there. This one is called face-centered cubic. Okay, that's how you read that one. It's face-centered cubic. And the aluminium atoms are on the corners of this cube. This is something the students made, and the atoms are at the corners, and electrons orbit the atoms. Bzzz, they are going around. Okay, well, okay, they don't make a buzzing sound, but they're going around. To make the electrons move is the meaning of conducting electricity. The electrons carry the charge. Everything has a charge, just as everything that exists has mass and is made of matter and has a size. So electrons have a size, have mass, and have a charge. So to make this electron move along a conductor, say in that direction, you would need to forcibly remove it from here, and then because it's got a charge and it's got magnetic field around it, it's going to jump on the next one, and it's going to be orbiting this one, and it needs an electromotive force to remove it from here. It's going to jump on the next one, it's going to orbit that one a few times, and it needs an electromotive force to make it jump to the next one, to the next one, to the next one. In a conductor, the electromotive force needs to be low to make the electrons jump, and in an insulator it needs a whole lot of force to make them move, budge at all. The electromotive force can be, it works like fractions. We're going to do fractions, alright? Say, for example, the electromotive force, I'm going to go with F. Force could be just a number, say 5. We're going to increase the force to 6 and to 7. Just 5 anything, 6 anything. You'll see. It'll make sense in a sec. And the number of electrons, because the electrons are either counted one by one or counted in bunches in coulombs. 1 coulomb of electron means 6.24 times 10 to the power of 18 number of electrons. So instead of that, let's go with 8 electrons. How about that? We're trying to move 8 electrons, okay? You have 3 fractions here, and so that's force and that's coulombs. This is not standard notation, but it's going to be the idea. You'll get the idea. Alright, so which one is bigger? 5/8, 6/8 or 7/8 as a fraction? Well, the biggest fraction is 7/8, 6/8 is less, and the smallest fraction is 5/8. Alright, if you want to move 8 electrons and you apply a force of 5, that's the easiest thing to do. If you want to move 8 electrons and you need to apply more force, then it's insulating more. And if you want to move 8 electrons and you have to apply a force of 7, then it's insulating even more. So a conductor would be little force to move any amount of electrons, and an insulator would be here a lot more force to move the same number of electrons. The fractions work the other way as well. If the force, this is still force, and this is still the number of electrons in coulombs or 1 by 1. Say we're going to apply a constant force of 2, and we might find that the amount of electrons that move when this force is exerted is 3 pieces of electrons, 4, that's 4 just a little lame, and that's 5. Alright, look at the fraction, look at it as fractions. Which fraction is the smallest? That 2/3 is more than 2/4, and 2/4, half, a half is bigger than 2/5. So when you have exerted 2 amounts of force and 3 electrons move, that means that it's that the electrons move slowly. When you exert 2 units of force and more electrons move, that means the electrons are moving easier. And you exert the same 2 units of force and even more electrons move, that means that the conductors would be located there. That means that the electrons move even easier. So the idea of calculating resistance is you're dividing voltage with amperage. Voltage being the electromotive force and amperage representing the number of electrons that need to be moved. So that's the meaning of resistance. Okay, you can also calculate resistance as a function of power, electrical power, and then those are the equations that you're using, but it's the same concept. How much force does it take to move how many electrons? That's what resistance is all about.